Hi, my name is Chris Mason, and in today's webinar, we're going to take an inside look at FDTD acceleration. I'll start with a little bit of background about Acceleware. We were founded in February of 2004 by two graduate researchers at the University of Calgary and three professors. They were investigating ways to improve the performance of electromagnetic simulations, and they were investigating high-performance computing platforms, including the FPGA and GPU. It turns out that the GPU worked extremely well for generating high-performance computations to complete electromagnetic simulations, and out of that the company Acceleware was formed. We're a publicly traded company on the Toronto Stock Exchange, on the venture branch of the exchange, and in around January of 2007, NVIDIA invested a significant, or provided a significant investment to Acceleware once they found out what we were doing with GPU computing, in the sense that we were using GPUs for high-performance computations as opposed to strictly graphics alone. And this was an exciting and novel idea, and something that they wanted to help fund and grow. Today we've grown from the initial 5 founders to 25 people, and we're headquartered in Calgary, Canada. Our core markets include oil and gas, electromagnetics, imaging, and in particular medical imaging, as well as linear algebra, which spans across a large variety of markets. The products that we provide are accelerated libraries that plug into existing applications to work with the underlying multi-core or massively multi-core hardware architectures provided by companies such as NVIDIA or AMD. From our customers' perspective, we provide them with software that abstracts the details of the hardware architecture so that they can plug in their software with their existing user interfaces to take advantage of the high-performance computations. Specifically looking at FDTD, or finite difference time domain, it's a widely used computational modeling technique. And what happens is they'll take a physical model of an object, say a human or a cell phone, or anything that they're trying to model the electromagnetic effects on, and they discretize it into small little cubes or boxes, voxels if you will, that they apply Maxwell's equations to get an accurate representation of how electromagnetic fields interact with that object. The idea behind that is if the model is good, it will reflect what happens in real life, in actual usage, and that's important for performance and safety. So the way Maxwell's equations work is there's iterative updates that are applied to the voxels, or the cell mesh, that alternate between electric and magnetic fields. And as you can imagine, depending on the size of your structure, you can get many millions or even billions of these tiny little cells that you need to model. The inside look at how we speed this up is by using our competitive advantage, which is really parallel computing. So because of the large scale of the simulation, the magnitude of the number of cells, many millions of electric and magnetic updates need to be performed for every time step. And what we do to speed that up is we take advantage of a massively multi-core processor, such as the GPU, to do many of them in parallel while performing transfers to and from the GPU memory. So while we're bringing in the next set of materials and cell meshes, we're continuing to compute with many threads and many cores on the voxels that we've brought into the processor. What this ends up doing is it provides faster end results for the end user, and significantly faster, sometimes an order of magnitude faster. To determine performance, typically, you need some sort of standard metric to calculate it. Ideally, you would just say, well, this simulation takes 10 seconds, but in the electromagnetics world, there's not really a standard simulation, and even if there was, people would approach the problem differently, so it's a little bit difficult to compare directly. To solve that issue, one way you can get a realistic comparison is to use what we term as a throughput metric of megacells per second, where megacells is the number of millions of cells that are processed in a simulation per second. It's calculated by taking the X, Y, and Z dimensions, so the number of cells along each axis, multiplying by the number of time steps, and then scaling it by 1,000,000. You also need to divide by the simulation runtime, the actual simulation wall clock time, to determine your throughput number in megacells per second. And what the next slide shows is the results of porting or running FDTD on a massively parallel platform such as the GPU. So in this case here, what we're comparing is the performance of 1, 2, and 4 NVIDIA Tesla GPUs against a 2-socket CPU-only performance. So using the CPU as the baseline, how much faster can we go on the GPU? And you can see in this diagram here, the blue line, which is a single GPU, performs somewhere, say, around 7.5 to 8 times faster than the CPU, which might operate at, say, about 100 megacells per second for a reasonably sized simulation. As you scale up using more cards, the throughput increases, as does the available size of simulation that you can run on the GPU. Our FDTD libraries are integrated with several software packages provided on this list, and you can find more information about this on our website at www.acceleware.com. But the idea here is that what you can do is you can purchase any one of these software packages from the partners mentioned on this list, and you use the Acceleware add-on to get performance out of the simulation. From the end user's perspective, it's a very seamless transition. The user interface stays the same. The only difference will be that you check hardware acceleration in a checkbox during runtime, and you see a performance improvement of 8 times or more, depending on the simulation you're running. The fields that are covered include electromagnetics, but it also spans into photonics, so we have partners in the photonics space as well. So sort of as a high-level summary, the core value is we provide hardware-accelerated solutions for more than just electromagnetics. It also includes reverse time migration for the oil and gas industry and Kirchhoff time migration as well, along with linear algebra solvers. On top of that, our libraries are cluster-enabled, meaning that they can also run on a cluster of GPUs. We typically work with NVIDIA GPU hardware and drivers, although we do look at other platforms as well. Some other nice features that you get when you use our libraries include diagnostic and setup tools, so easy ways to troubleshoot and set up your system. It detects automatically if you have a valid graphics card and if the drivers are properly installed. And as well, because we're intimately tied to the hardware, we have lots of experience and background on system integration. So how it best fits in a server room or would fit at your desk side, for example, what might be some good partners to work with from the hardware vendor side of things. The main customer benefit is access to speed. It allows you to connect time-critical applications to multi-core processing. So being able to leverage multi-core or massively multi-core hardware to improve speed without having to understand how it works or be required to re-engineer your application to fit that model. From a business perspective, what it ends up netting for the organization is it really speeds up product design. So we have people who use this on a regular basis as part of their design flow, and they can decrease their time to market significantly. So oftentimes simulation in say a cell phone design might be on the critical path in terms of bringing the product to market, but when you can speed up that time by a factor of 8, you can bring your product to market that much quicker. Product quality is also something that the customer benefits from. So instead of simply bringing the product to market quicker, you can repeat iterations and test different scenarios, different positions of the model, for example, and allowing you to run multiple iterations to optimize the design. And same with the data quality, which is similar to the product quality. More computational capacity allows you to get finer resolution on your models, which gives you better access to or it gives you a better match of your simulation to what will happen when the product is in the field. There's a lot of flexibility in form factors and how these libraries can be used. They can be used at your desk, so on your desktop computer, where you would either have a card or a desk side unit sitting beside your machine right at your desk that you wouldn't have to share, for example. Or for organizations with large IT departments that coordinate resources across the company, there's server form factors where you can submit your jobs to a queue into the server center, and that will run on the GPU and return the results back, so you get full usage of your hardware. It also makes it cost-effective supercomputing, specifically relating to power and space. So to get an equivalent cluster of regular CPU units to match what the GPU can do, there's a significant space and power requirement that's associated with the CPU-only version that the GPU will circumvent because it has a better performance to power footprint. On top of that, it's driven by mass market technology, in particular video rendering and video games for that matter. So because of that, there's a lot of innovation that goes on, and the parts and hardware are continually improving. The other benefit to taking or to using our libraries, to using Accelwere's libraries, is that we future-proof applications in the sense that you don't have to worry about the underlying hardware architecture. It changes fairly regularly. Architectures change. And as a customer, you don't have to worry about the underlying architecture. The integration is done once up front, and following that, future changes to the hardware are abstracted from the customer. So thank you for your time. If you have any additional questions about this webinar or would like to learn more about our products, you can direct your questions to myself, which is chris.mason@acceleware.com. And you can also visit www.acceleware.com for more information. Thank you.